Hi, I'm Sandy, the systems engineer here. Today, I'll be introducing some of the features and improvements in our Enterprise Edition 5.2 release. The main focus of 5.2 is to enhance the stability of our ultra-large-scale clusters. At present, it should support at least 100 billion files. The second point is network optimization for distributed caching. When performing AI training, there will be significant improvements in data read performance. In practice, we can achieve at least terabyte-level aggregate bandwidth. The third point is that we've released a Windows client, which is actually similar to what we have in our Community Edition. At the end, I'll also briefly introduce some other important features to everyone. First, we can support an even larger scale over 100 billion files. As you can see here, there is a chart which actually comes from one of our internal tests. When we conducted this test, the monitoring chart recorded that the number of files had already reached 135 billion. So why do we need to conduct this test? It's because many of our current users are in AI scenarios where the number of files is growing extremely rapidly, especially for users working on autonomous driving. In our production clusters, it's actually very common for a single namespace to exceed tens of billions of files. In fact, our largest one has even surpassed 50 billion files, and it's still continuing to grow. As a service provider, we definitely need to proactively test the capabilities of our product in advance. So we arranged an internal test of at least 100 billion files in scale. Yes, this test was conducted on Google GCP. As you can see, the entire hardware configuration consisted of 36 nodes, each equipped with approximately 176 CPUs, 704 gigabytes of memory, and a 100 gigabytes network card. Right. In this setup, since these nodes are mainly used to deploy our metadata services, the most critical resource is memory. So in terms of software, we actually deployed 256 partitions, and each partition runs 3 metadata service processes. Then this form a RAF group, so it's quite straightforward here. I can briefly introduce the architecture design of our Enterprise Edition metadata. At its most basic, it's actually just a single partition. Typically, we deploy 3 services, which many of you are probably familiar with. This forms a consistency group, a RAF group. Among them, one acts as the leader and provides services externally, while the other 2 serve as backups, and to ensure the consistency of certain critical data. Generally speaking, in GCFS, all metadata resides in the memory of the metadata service. Therefore, when the number of files becomes very large, it will inevitably be limited by the available memory. So under normal circumstances, we try to keep the metadata for a single partition within 2 billion files. In practice, when the number of files exceeds 1 billion, we start to consider whether we should switch to a multi-partition setup. So what exactly is the concept of multi-partitioning? If you're familiar with file systems, you know that many file systems, including open source ones, have similar approaches. Essentially, they split the index within a file system for separate management. We do something similar, dividing the namespace so that one part of the index is managed by partition 1, and the remaining part is managed by partition 2. And so each partition manages a different part of the index. By working together, all the partitions collectively manage the entire file system. This approach achieves horizontal scalability, allowing for management and migration, and potentially even supporting capacities beyond the trillion files in the future. In our test, we divided the system into 256 partitions. To put it simply, each partition handled about 4 to 500 million files, so our processing capability was more than sufficient. For our testing tool, we used the internally customized tool similar to MD Test. The advantage of this tool is that it can connect directly to our metadata service, bypassing the kernel and fuse layers, which allows us to achieve even higher performance. The basic logic behind it is to create files and write some data to them. Let's take a look at our test results at that time. The entire process, starting with the write phase, took about 12 hours, during which we wrote a total 1.3 billion files. Here's a chart. There might be something a bit odd here. There's a drop at this point. That's because we actually ran the test twice. We were using a spot instance on GCP for the test, which is a preemptible instance. So during the first run, halfway through the run, the instance was reclaimed. So we had to rerun the test the next day. That's why the ladder line on the chart is probably more accurate. Overall, it took about 12 hours. And in the end, we wrote 131 million files. If you do the math, that's roughly 3 million files written per second. When creating each file, at least 2 operations are involved. File creation and data writing both require accessing metadata stored on node 19, so at minimum 2 requests per file throughout the entire writing process. Due to metadata's nature, the cluster's processing capacity is roughly stable at around 8 million QPS. So it should be 300 times 2 plus some additional operations such as looking up directories and other related tasks. Therefore, the overall QPS for our metadata is about 8 million. After writing these 130 billion files, we continue to apply pressure by adding some loads that we consider to be fairly typical. We ran a mixed workload for more than 24 hours, and during this process, we observed the overall performance of our metadata. Looking at the results, the system remained quite stable. Here are 2 more data points. First, we measured the average latency of our metadata requests from the client side, and it was typically around 1 millisecond with no noticeable lag. This result comes from our, this is pretty much in line with our expectations. Another point is about our service process, as mentioned earlier, the RAF leader, which is actually the element process providing the service. Its memory performance shows that the average metadata size per file is only about 100 bytes, which from our perspective is also an expected result. By the way, regarding the RAF group for our metadata, aside from the leader, the other 2 nodes are typically set as hot standby and cold standby. As for the cold standby node, it mainly stores logs and participates in RAF elections in a simple way, so its memory consumption is actually quite low usually. Maintaining around 100 megabytes is sufficient. The hot standby, on the other hand, needs to be ready to take over at any time. So since it needs to be ready to take over the service at any time, its memory consumption is also relatively high actually. It's quite close to that of the service node. However, the advantage is that because it doesn't need to directly provide services, it can perform more aggressive memory compression. In fact, its average metadata size is likely to be a bit smaller than that of the service node, right? So overall, if we consider all 3 types of metadata services together, the average size of a single file's metadata should be less than 200 bytes. It doesn't simply multiply by 3, so actually we've made some improvements in this area before as well. Okay, aside from the scale migration, another important performance improvement we made is our distributed cache. Because from a cost perspective, most people would typically choose object storage for the persistent storage of all their data. However, when your data volume is large, for example, many of our current use cases involve tens of petabytes at this point. In order to keep costs down while also ensuring sufficient bandwidth during training, most users will consider setting up our enterprise-level distributed cache. The overall performance of this distributed cache directly affects the efficiency of our training process. So this distributed layer is also extremely important for us. In terms of performance, our testing is similar to before, actually using the same hardware configuration. But this time we actually chose 100 nodes, with each node equipped with 2 NVIDIA cards that support 5 gigabytes of independent bandwidth. Overall, we hope that in theory, this setup can provide at least 1 terabyte of bandwidth. As for the software configuration, we simply group all the nodes together directly. This formed our Enterprise Edition distributed cache cluster. For testing tools, we use the commonly seen file tool. We chose a 1 megabyte block size and performed sequential read tests. The goal was to push the hardware to its performance limits. Looking at the final results, we can see that the aggregate read bandwidth exceeded 1 terabyte, which is already quite close to the theoretical maximum bandwidth of the network cards, since each node only has a single 100G network card. In terms of configuration, both the CPU and memory are actually more than sufficient. Yes, the main reason is that since we're using cloud-based machines, the setup is designed around this network card. So overall, the final result is that at least with this configuration, we can achieve around 1.2 terabytes of sequential read bandwidth. In fact, we've done a lot of work here, aside from some of the other aspects. In terms of details, aside from measures to improve performance, we also approach it from another angle, namely to reduce our overall CPU consumption. That is, the amount of CPU required per gigabyte of bandwidth is also a key concern for us. Here, one approach is to adjust the network socket configuration to address CPU waste caused by network fragmentation. We also use some common network optimization strategies, such as multiplexing in specific scenarios. Ultimately, we've managed to reduce the CPU consumption per gigabyte of bandwidth on the client side from over 2 cores at 5.1 million to possibly just 1 core now. Yes, in addition, on the cache node side, we mainly adopted some zero-copy technologies. On the cache node side, which essentially acts as the server end of our distributed cluster, we managed to reduce the CPU consumption per gigabyte from what it was before. Yes, it was reduced to less than 0.5 hertz. There are actually many more details regarding the optimization of this part of the network, and later on, my colleague Liu Qing will give a more detailed introduction. Also, there's another thing, which is our Windows client. As Kai-Ming just mentioned, this is something available in both our community and enterprise editions. Previously, our community edition has always been open to the public, but for the enterprise edition, there have always been some usability and compatibility issues. After careful consideration, we have not made it publicly available until now. This year, in version 5.2, we had dedicated colleagues fully commit to making many improvements to the Windows client. At the very least, we have fixed some compatibility issues with the client in areas such as certain API calls and user identity management. And we have also improved our overall tool support. These are actually some built-in subcommands that we provide. This includes debug state info. Yes, if you've used the community edition, you should already be quite familiar with these features. It's just that previously, many of these commands couldn't be used on Windows. Now, they all work properly on the Windows platform. Another improvement is that we've added support for background running parameters for the Windows client. This way, FA can be directly mounted as a system service without needing to rely on third-party tools anymore. Overall, our internal testing shows that the Windows client is already in a usable state for simple, everyday scenarios. So now we're releasing this beta version to the public. I think anyone interested is welcome to try it out and give us some feedback. We'll also actively cooperate if there are any issues. So we will make active improvements. We hope that users who need to use it on Windows will also have a good experience. Okay, finally, there are some other important feature optimizations. There are actually quite a few here, but considering the time, I'll just give everyone a brief introduction. One of them is feature improvements for the Python SDK. As mentioned, this is also available in the community edition. In the enterprise edition, version 5.1 was already released. In version 5.2, we've improved its compatibility and performance, making it easier and more efficient to use. As for shared block devices, this is a feature unique to the Enterprise Edition. It mainly allows you to use certain cloud-based block devices to provide write acceleration capabilities. Previously, this feature had specific hardware requirements. We needed the block device to support multiple mounts, and each client might need to mount a large device. Only after a client writes to it can other clients read from it. There is actually a specific requirement for these block devices, which is multi-mount support. In version 5.2, we made some improvements to these features. Now, as long as a block device can be mounted locally, that's sufficient. Our clients can access the block device through their own network. There's no longer a strict requirement for multi-mount support. This feature, on-demand import, is also one of our Enterprise Edition features. Our Enterprise version already supports the import function itself. For example, if there's already an object on the storage, we can import it. Using our commands, you can import it into the Enterprise Edition, create necessary metadata, and bring it under our management. This way, users can access objects across different protocols. They can use the file system interface to directly access the original object in storage. On the other hand, you can also use the caching capabilities provided by our JuiceFX to achieve certain acceleration functions. Now, on-demand import refers to the import feature we just mentioned. When there are already a huge number of objects in your storage, for example, some users may have an extremely large system with certainly more than 1 billion or even tens of billions of objects. So this import process can actually take a very long time, and for users, they might not need everything right from the start. Therefore, we have now implemented an on-demand import feature, which means you just need to specify, okay, I need the objects from this system, and only when we actually access them will the import action be triggered. So this is a feature we have improved in version 5. Right, and there's also support for cache disks of different sizes. This is actually relatively simple. Previously, when each client used local caching, we require that all disks be the same size. In some heterogeneous environments, this wasn't very user-friendly. Now, by applying a weighting mechanism, we can indeed support different cache disk sizes, allowing everyone to use their cache disk regardless of size. Next, there's also an improvement in stability, one aspect being read amplification. This is because, for performance reasons, JuiceFS has implemented a number of specific read strategies. It's possible that in our expected scenarios, there is indeed a significant improvement in read performance. However, in some products that are not quite suitable, it can actually lead to read amplification, which ends up wasting object storage bandwidth. In this version, we have revisited some of the related prefetching strategies and improved the issue of read amplification in many scenarios. Another aspect is the global QoS capability, and this is because in our Enterprise Edition, each client requires a specific token when using the system. This token restricts the client's read and write access capabilities. If multiple clients have the same requirements, for example, if they all need read-write access or all read-only, they can share a single token. Based on this access token, we have implemented a global QoS capability, which allows us to collectively limit, for example, the overall read or write bandwidth for multiple clients. With this kind of global QoS capability, there were no issues when the scale was small at the beginning. However, as the user base grows larger, not only does the number of files increase, but another issue arises. The number of clients mounting and using the system also rises rapidly. So when you have a large number of clients, in order to maintain this global state, the related maintenance messages become extremely frequent, which to some extent can impact our overall operations. In this version, we identified this issue and implemented an optimization. The main improvement is that certain messages within a single client can be aggregated, which results in a more stable and effective global QoS bandwidth limiting capability. The remaining aspect is usability. These two features are actually quite similar. The main point is that you can upgrade a client with one click through the console and also retrieve a client's debug information with one click. For those who are familiar with it, you should already know about these features. In CFS, there's actually a debug subcommand that can collect relevant information with one click. We gather some of the most useful log information. Previously, due to the architectural design of JuiceFS Enterprise Edition, we actually couldn't access the user's client from our side. So whenever we needed to upgrade the client or troubleshoot issues and collect client information, we always had to rely on the user's cooperation and have them help us with these tasks. In fact, throughout the entire process, the efficiency wasn't particularly high and it wasn't very convenient. Now, in version 5.2, we've also made improvements to the console so that we can select the required clients directly from the console to perform one-click upgrades and one-click information collection. This way, whenever you need to use these features, it becomes much more convenient. In addition, we've added new commands, mainly to help users recover files from the recycle bin in specific situations. For example, you can filter by keywords, or if you provide me with a specific list, we can do that as well. Accelerated recovery is also an auxiliary tool. And finally, we've made improvements to our security, with the main change being that encryption for storage access credentials is now enabled by default. This is especially important for many users, particularly those using our Enterprise Edition, because the AK, SK for object storage is very sensitive key information, and if it were to be leaked, the impact on them could potentially be catastrophic. So starting from this version, we will apply advanced AES encryption to all access credentials, and it will be enabled by default. Basically, users will not be allowed to disable this feature, which we believe will significantly improve overall security. So those are the main important features of version 5.2. Thank you all for your attention.